As discussed before, nuclei change to become more stable. The more stable the nucleus, the bigger the change. The bigger an atom, the more stable it can be. In this podcast we will discuss the changes brought about by alpha, beta and electron capture and how they move nuclei around the neutron-proton graph. Alpha decay is the biggest energy change a nucleus can undergo. The nucleus of an atom loses a whole other nucleus of a different atom, the helium nucleus, 2 protons and 2 neutrons. This change can be shown using a general nuclear decay equation. As with all elements, the number of protons a nucleus has determines the chemical properties of an atom, and therefore its chemical symbol. If a nucleus has 92 protons, then it is a uranium, irrespective of the number of neutrons. This number is very important and so has its own symbol Z. This goes at the bottom left of a chemical symbol. The size of a nucleus gives it its mass, and so in chemistry, the atomic symbol has a mass value given by A at the top left of the symbol. As long as this number is simply the number of protons and neutrons together, we can work out the number of neutrons in a nucleus. More often than not, this number represents the average number of nucleons, protons and neutrons of an element, so includes all the number of neutrons in all the isotopes as well. We don't want this. So for our purposes, and because we are dealing with all nuclei, this symbol will represent a whole number combining the numbers of protons and neutrons for this particular nucleus and be called the nucleon number. For an alpha decay, the nucleon number A will decrease by 4 because the nucleus is losing a total of 4 particles, and the proton number Z will decrease by 2 as we are losing 2 protons. The decay equation is the original element and its nucleon and proton numbers with an arrow leading to the other side of the equation. This side of the equation contains a new symbol for the new element with a nucleon number A minus 4 and a proton number Z minus 2. This new daughter nucleus also has a helium nucleus with it, so the equation has a plus He with nucleon number of 4 and proton number of 2. The alpha decay therefore will move an unstable nucleus by 2 points down the y-axis, the neutron number, and 2 points across the x-axis, the proton number. Alpha decay moves the nucleus diagonally towards the origin, 0, of the NZ graph. Beta decay is in 2 forms, so has 2 different equations. Beta minus decay changes the neutron to a proton and emits an electron. Because the neutron is changed to a proton, the number of nucleons doesn't change. That means the A number doesn't change. However, the number of protons does increase, so the Z number goes up by 1. In an equation, you have the original symbol with its original Z and A numbers. Again, there is an arrow showing that the nucleus decays, but this time it leads to a new symbol with the same A number, as the number of nucleons doesn't change, but with Z plus 1 as its proton number. An electron isn't an element, so we need a new symbol to show this. We choose a lowercase e to stand for an electron, with a uppercase minus at the top right hand corner if you wish. This electron has to be consistent with the rest of the equation and show where the different aspects of the equation has gone to. So even though an electron doesn't have a number of protons or nucleons, it still needs a value for these numbers to show what happens. This also conserves mass and charge. The nuclear number for the electron is 0. As the change from a neutron to a proton hasn't caused the change in nuclear number of the original nucleus, the proton number does represent the change in the original nucleus and is given as -1 to show that the charge has been conserved. Z plus 1 plus Z minus 1 equals 0. The decay on the NZ graph is shown by the nucleus moving away from the origin along the x-axis, the proton number, by 1 unit, and moving down on the y-axis, the neutron number, by 1 unit again. Beta minus decay moves the nucleus diagonally down and right on the NZ axes. Beta positive decay changes the proton to a neutron, so is opposite of beta plus decay. Whereas before, the equation changed to have a Z as plus 1 on the new daughter nucleus. Now, the daughter nucleus has Z minus 1. The nuclear number again stays the same. The accompanying positron symbol needs to balance the mass and charge of the beta plus decay as before, So the symbol for the positron is still an E, but now with a plus symbol if you want, and a Z value of +1. The A number stays 0. As before, the nucleus is moved diagonally across the NZ graph, except this time the nucleus moves up and left to show that the proton number has decreased by 1, but the neutron number has gone up by 1 as well. Electron capture has two elements on the initial stage of its decay equation. It shows the original nucleus with proton and nuclear number, plus the symbol for the electron from above, an E with a nuclear number of 0 and a proton number of -1. After the arrow, the parent nucleus is changed so that the proton number has gone down by 1. The proton has turned into a neutron, so the nuclear number stays the same. The daughter nucleus has a symbol with nuclear number unchanged and proton number decreased by 1. There are no other symbols on this side of the equation if you ignore neutrinos. On the NZ graph, the nucleus moves in the same way as beta plus decay. The Z goes down by 1 and the N goes up by 1.